So it's really great to have Albert here. Albert is a postdoc at Georgetown. He was, until very recently, a PhD student at Northeastern. He's going to be telling us about private histograms in the shuffle model.
All right. Thanks, Thomas, and thank you all for coming today. As Thomas said, I'm Albert, and today I'll be talking about differentially private histograms in the shuffle model. The model has seen a lot of activity in recent years, and I'd like to go over some of my own work in the topic. So big picture, we're going to talk about two protocols with different design goals. The first optimizes like asymptotic error, and the second is built with some implementation considerations in mind. And the second protocol has some bonus features that I'll also talk about. All right, so to start the talk, I'll define some terms. Users are those people with raw personal data that we want to keep private. An analyzer is something or someone who wants statistics on that population. And we'll consider adversaries who want data on an individual level. And again, as standard, we'll consider the central model where the analyzer is entrusted with all the data. And they run a private algorithm so that the adversary can't learn individual user data. And meanwhile, in the local model, users don't trust the analyzer. So they each execute a local randomizer, and this is the private algorithm. The privacy barrier is around each user. So the output of each randomizer is something I'll call a message that we send to the analyzer. And because of privacy, these messages are randomized, but as a consequence, the analyzer gets weaker signals than the central model. You don't have access to direct accounts, for example. And so these are negative results that are known in the literature. And these cause us to have an important question. And the important question is, can we get low error private statistics, like in the central model, but just low trust? Not so much as in the central model. And so my work has shown that the answer is yes. I focused on the shuffle model. And here users don't trust the analyzer, but trust the helper to do a simple job, which is to shuffle messages. And it is indeed known that less noise is needed than a local model, such as for histograms, as we'll see. Conversely, more noise is needed than the central model, such as for parity learning. I won't talk about these lower bounds, but I'll focus more on these upper bounds. And so the model has its roots in work by Battelle et al. And was also defined in my work. And so what is this model more precisely? Well, it bears some resemblance to the local model in that there is a local randomizer run on user data, and there's an untrusted analyzer. But this time there's a service or functionality called the shuffler. It takes in user messages, these Ys, and it outputs some random permutation. So the first message of user 81 can end up on top, followed by the second message of user 27. And notice that we're allowing multiple messages per user. It's like everybody can drop off like 2 envelopes or more in the mailbox, and the post office is just processing them in some random order. Right, and the important thing to note is that we're designing the randomizer such that the big box I have here is privacy preserving. We have n executions of the randomizer, followed by a shuffle. And unlike local privacy, we don't really care how private R is. We only care about the output of the shuffler. All right, so one way to implement the shuffler is with a combination of onion routing and some randomized delays. And so what we have here, we have that some user encrypts data like layer by layer. And so as it passes through a network, you decrypt and decrypt, and at the end, you get the raw plain text. And so notice that in this diagram, well, as long as node 5 randomizes, node 8 can distinguish the red and blue messages. And of course, they don't know the path they took because it was also randomly chosen. The only recourse for an adversary is to somehow break the encryption, but that requires having all the keys in the path. And another thing to observe in this implementation, at least, the number of messages determines the encryption time and the network load. Right, sending more messages increases the network load. And so it's kind of better to have a few dense messages than many messages that like require padding for your encryption. Right, so it's better to have a few long messages than like many short ones, roughly speaking. Right, so why study this model? Well, there are some nice properties of this particular architecture. One thing is that it's reusable and general purpose. We don't change it for every problem we're solving. It's just like a fixed like, pipeline, basically. Another thing is that the shuffler could be used by multiple protocols at once. Because communication is encrypted, A and B can talk to the user simultaneously through the same intermediary. And so this is kind of in contrast to a secure aggregation model where like you kind of normally envision the intermediary as adding up messages instead of shuffling. So there it's not as obvious if we can do like simultaneous computation with the same intermediary. And the final, more theoretically interesting property is that shuffling bits is like the same as adding bits. If I observe a bag of zeros and ones, like all the information that's contained is like the counts of ones. And this is very neat because it implies simulation of centrally private algorithms, but without having to go gate by gate, for example, through a circuit. And you have to avoid like using MPC to evaluate each circuit or each gate or part of the circuit. All right, just to make sure we're on the same page, I'll be using the epsilon delta definition of differential privacy. Epsilon delta are parameters that define the closeness, and it's a hybrid multiplicative and additive constraint. And so like that's most of the words in my title. I've covered privacy, I've covered shuffle model. So like all that remains is histograms. So like in this version of histogram problem I'll study, each user has some discrete value. And the goal is to privately estimate the counts of each domain element. We'll try to minimize the L infinity distance, the maximum error of any bin. And in the central model, error due to privacy depends only on epsilon and delta, whereas in the local model, we have dependence on both N and D. This is work by Bussey and Smith. And as an aside, our objective is a little bit different than the work by Feldman, McMillan, and Talwar, which also study shuffle private protocols, but they kind of optimize L2 error of distribution estimation. And we optimize like a different metric. Taking all this together, all this setup together, we have a two-part question. Can we get low error private histograms in a shuffle model using few messages? All right, so my work, I've worked with Victor Balser and Maxim Giliev on two solutions. What's so interesting about these two solutions? Well, the first is interesting because its asymptotic error is close to the central models. And the other only demands a constant number of messages per user. There's an asterisk on this constant because there's a mild constraint on the input size that I'll get into later on. But the second property that I'll talk about is that we have resilience to malicious users. If a user wants to bias the computation, that bias is bounded. Right, so we have two results, and I'll put these in a table. So in the first row, we have the Cheu protocol, which achieves error that depends only on epsilon and delta, but at the cost of like D messages per user. And again, like this can be very bad if you want to implement it in that mixed network that I described earlier. At the other extreme, we have this second protocol, which only demands like 2 messages per user. This is like basically as low as it gets, but the price is a logarithmic dependence on the domain size. One thing to note
Can
is
you
that
interpolate between these settings?
can you repeat that?
Can you interpolate between these two settings? Like,
Sure, yeah, I'll fill in the table. There's like other protocols,
okay.
but like these are the ones I focus on in this talk. Right, so just to note that like the first protocol, in comparison to Essential, we're only off by like an epsilon factor. It's 1 over epsilon squared versus 1 over epsilon. And in contrast with the local model, we don't have an explicit dependence on the root n, and we also don't have a dependence on domain size d. So that's like very nice. And like as Thomas mentioned, there's like other protocols by other people, and work by Ghazi, Gulwich, Kumar, Pa, and Blinker. I have logarithmic dependence on domain size and error, but like slightly more messages than what we achieved in the Cheu paper. And there's yet more work that I can't really fit in this table, but there's follow-up work by Ghazi, Kumar, Manrang, Sempa that also, again, achieve log D error, but like vanishing number of messages per user. So as n increases, the number of messages decrease. But it turns out like our rate of decrease in our protocol is actually faster. Right, so their rate was d over n. Our rate actually turns out to be like log d over n. Right, but I'll focus on the 2 extremes for this talk. Right, so like the first extreme was near optimal asymptotic error by Balser and Cheu. So in this protocol, the core idea is to perform parallel counts. We run a counting protocol, d times in parallel, 1 for each bin of the histogram. And just as a sidebar, like this was also presented in work with Smith, Ullman, Zeber, and Zilio. And so what I mean by this more explicitly, well, each user does the following. You run the counter randomizer on the indicator bit that indicates if your data is j for every j in the domain. Right, it's very simple, just count things. But then we're going to have to label each message with the index j. So if you produce some message y, it gets turned into a tuple j comma y. And all these tuples are sent to the shuffler. And so like, why do we create these tuples instead of just sending these messages? Well, the analyzer has to compute on these messages. And like these labels help us distinguish which execution we're looking at. Right, so you run the algorithm A on messages labeled with j. Right, that's how we estimate the count of j. Right, so the nice thing about differential privacy is that it's closed in composition. So like whenever the counting is private, the histogram protocol itself as a whole is private. And we can get a bound on error from a union bound over the executions. So really all we need is a way to privately count in the shuffle model. And like to give some context to like counting or private counting, let's look at other models. And so in the local model, the error scales with root n, but in the central model, if you use the Laplace mechanism, we just get 1 over epsilon. Right, that's very classical results. But notice that if we change from Laplace to another mechanism called the binomial mechanism, we get a little bit worse error. We have this log 1 over delta term. But like, what's this alternative mechanism? Well, the binomial mechanism is the following. You add a sample from binomial noise to your true count. And like this binomial distribution is calibrated such that the variance mp times 1 minus p, it's this function of epsilon and delta, right? So this is what gives you this 1 over epsilon squared root log 1 delta in the error. Okay, so I've been talking about counting in other models, but we're talking about counting in the shuffle model. Like, why did I take this sidebar about the binomial mechanism? It's an essential model. Why do we care about that? Well, the idea is to simulate the mechanism, right? And once we simulate the mechanism, we can just get the same error, which is like 1 over epsilon squared log 1 delta. And we could be done here, but we'll actually add another step to our protocol. The next step is to perform a special truncation trick. It will introduce a little bit of bias, but it turns out it will be worth it. But for now, let's focus on this simulation of binomial mechanism. How does that work? Well, the simulation works as follows. We send the user's bit along with a random bit, x of I, coupled with Bernoulli p. So the shuffler will permute all these bits uniformly at random, right? So that means that the view is just a bag of zeros and ones, right? So the analyzer just sees zeros and ones. They know the number is 2n, and the sum is just the noisy sum, right? And so, but why is this important? Well, it's important because, as I said before, you can simulate the view from the count, right? Once you have zeros and ones, all you need is the counts to create that bag of zeros and ones. So the protocol itself is going to be private as long as the noisy sum is private. And we already know how to do that. There's the binomial mechanism, right? Just set the variance to be big enough. And because the variance scales linearly with n, when we solve for the parameter p, we can get that p is 1 over epsilon squared n for epsilon delta privacy. All right, so the probability of getting a 1 is very low. So that was our first step, simulate the binomial mechanism. And again, this works as a building block for histograms. Just run it each for every bin. But as I said before, we have a second step, which I'll explain later, called a truncation trick. But for now, let's just understand that it has 2 properties. First, if the input is all zeros, the error is 0, probability 1. Otherwise, the error is a little bit larger than 1 over epsilon. It's 1 over epsilon squared, and you have this log factor. All right, so we have simulation and then a little post-processing. That'll give us some extra properties. Why do we care about these properties? Well, let's visualize, let's use a visualization to see why this is useful. Remember, we're performing binary sums in parallel. So we have, for every bin in histogram, we're counting. So the protocol is adding noise to the non-empty bins, the bins of actual elements in them. But it's not adding noise to these empty bins, the ones where count is 0. This is interesting because there's at most n non-empty bins, because that's the number of users. So that means that randomness is only occurring in n executions. So we have union bound over n executions, not d executions. So we have a log n instead of a log d. All right, so, and when delta is sufficiently small, the bias term dominates these two the summation. Right, if delta is smaller than 1 over n, then 1 over delta is smaller than n. Right, so this all works provided that we have this property where there's no noise in empty bins. So how do we get that? Well, we have to rely on 2 key facts. The first key fact is that the analyzer's view is a noisy version of count, where the noise is binomial. And second, the binomial is bounded. The noise is never larger than n. So if the count is 0, the noise count is never larger than n. And so the modified algorithm is just to report 0 if you're less than n. Otherwise, you just debias and report like an estimator that's like non-zero. And again, this introduces bias because values could be erroneously truncated. Right, so in total, that gives us that 1 over epsilon squared log delta error that's very close to central, but at the cost of having to execute a protocol basically for every bin in the histogram, even if it's empty. So we have like D executions, which means D messages per user, at least. Right, so like how do we get around that? Well, we can actually reduce it down to 2 messages per user. So that takes us to our second protocol by Cheu and Ziliev. Right, so we have low message complexity, 2 when n is sufficiently large, so polylogarithmic in D, and also polynomial 1 over epsilon and log 1 over delta. And the second property that I'll talk about is that estimates are robust to malicious users who want to bias the computation. And if I have time, I'll also talk about some secondary properties that I'll talk about later. Right, so the technique we'll employ is fake users. Okay, that's a term we made up, but like, what does that mean? Well, each user is going to do the following. They encode their value as a one-hot string. So if your value is 3, you put a 1 in position 3 and 0 everywhere else. Right? Very basic thing. And then you just flip each bit with a small probability q. This is basically randomized response. This is like a local protocol, locally private protocol. So why is this interesting? Well, the interesting thing is that we have another step, which is to construct extra strings of all zeros. And then we flip those bits the same way. All right, so what's happening? Well, what's happening is we're running randomized response on real data and also running on k fake inputs. Then we send all these randomized strings to the shuffler. And then the shuffler shuffles. And then the analyzer computes on all the strings it sees, right? And it obtains some unbiased estimators. And the way it does so is like in the same way as in the local model, where we just do some linear function on the sums.
So would this be k plus 1 messages, or what's happening?
Right. So like they're k plus 1 separate strings, each is like a separate message.
And each should be a separate message.
Right.
Okay.
And notice that right, we have a parameter k, we also have a parameter q. And small q ensures low error. So like when q is like vanishing with like the total number of strings, and the total number of messages, I should say, the expected number of flips is low, right? For each bin, it's like constant, if it is that small. Okay, but the question you might be wondering is like, why bother with these fake users? Why can't we just use the real user data and like somehow shuffle just the real user data and then just not have these fake users? Well, it turns out we run into problems. So like what goes wrong when k is 0? We'll find out. So we'll find 2 inputs, all 1s, and then a 2 followed by all 1s, right? X and X prime. And what we'll show is that the adversary will be able to distinguish these 2 cases if q is that small and k is 0. Right, so in the first case, user 1 does this encoding, a 1 followed by zeros. In the second case, you have a 0, 1, and then all zeros. Right, this is just basic one-hot encoding of your data. Now, in either case, any other user encodes just 1, so it's 1 followed by zeros. Right. Now, this is only the first step. The second step is to randomize. And so in the first case, the user reports a string drawn from this like product distribution, Bernoulli 1 minus q and Bernoulli q's. In the second input, you have a different distribution. You just shift the bias toward position 2. And then any other user in either case sends this first distribution, or samples a message from this distribution. Notice that the bits after position 2, like they're independent of the user and the data. So they're really not really contributing anything to like, they're really not revealing information about users. So we'll just ignore them for our privacy analysis. So now we want Q to be small. We want Q to be like 1 over n to give us like very low error. But like we find out this is a problematic because in the first case, user 1 likely reports 1, 0 because of the bias. In the second case, user 1 likely reports 0, 1. Okay, these are 2 different inputs, 2 different outputs. And in any other user in either case reports 0, 1 with very small probability, q squared. So it's like 1 over n squared. That's very small. And let's visualize why that's bad. We have 2 worlds, the shuffler, the output on input x, input on x prime. So on user 1 sends either 1, 0 or 0, 1. And then everyone else sends, like, also sends strings. But the point is that, like, they distribute it in a bad way. Most people send 1, 0, and a few send 1, 1 and 0, 0. But the point is that, like, basically nobody sends 0, 1. So you can easily distinguish the 2 cases. All right, so user 1 is indistinguishable from any others in the first input. But in the second input, like, user 1 is like unique. So that's not good for privacy. All right, so if we insist on this small q, we'll need fake users. And so if there's non-zero number of fake users, they'll be reporting a string drawn from Bernoulli q, because they have 0, 0, and they flip with probability q. All right, why does this matter? Well, it makes a world of difference because it places equal mass on 1, 0 and 0, 1. So user 1 can't hide better in one case than the other case. And this holds like without loss of generality, no matter what pair of inputs you create. Right, so all these fake users provide like cover noise for these for this hard case. Right, so to visualize, like going back to our picture, we have extra values, these question marks, and like they'll serve to blend these 2 cases together. All right, so focusing on the box messages, which are from either user 1 or these fake users, we can just reason about the distributions. So, all right, so a fake user sends either 0, 1 or 1, 0 with some probability, and we can compute this probability from the distribution. And so the expected number of these like cover noise is 2q times 1 minus q times nk, because there's nk fake users. And so we expect this amount of like cover noise. And so conditioning on having this amount of cover noise, like half are 0, 1 and half are 1, 0. And again, that's from the symmetry of the distribution. And so like we're almost done with like our sketch of a proof. Let's like visualize it another way. So we'll represent the messages as counts. So like in one world, like the count of 1, 0 is like a 1 because user 1 likely reports that value. In another world, user 1 likely reports 0, 1. And all this cover noise is either 0, 1 or 1, 0. And I'll represent them as purple bars. And so the thing is that like the purple bars are half and half between these two values. So it's binomial m 1/2, right? M is number of cover noise, and 1/2 is whether or not you're in one bin or the other. But notice that the count in the other world is 1 plus that binomial. Okay, because like of the user one. So we have two bars, and like they distribute it in like very similar ways. It's 0 plus a binomial or 1 plus a binomial. So we just invoke the binomial mechanism again. Very nice. You don't have to prove anything new, really. So as long as the number of cover noise is sufficiently large, we get epsilon delta differential privacy. So we have two equations regarding this amount of cover noise. And so we can combine these two equations and like solve for our parameters. And what we get is that we can assign our Q to be vanishing with nk, right? Just solving for a Q. And you just need n to be sufficiently large so that it's like less than 1 to be a valid flipping probability. All right, so like that's privacy. How do we actually get estimates? Well, it's not too complicated. You have a set of strings or messages. And if a string came from a user value j as a 1 at nxj with probability 1 minus q, and otherwise the probability is q. And you can model the random variable. Well, you can create a random variable called tj, which is just the count, right? So it's just a sum of two binomials. Right? And you can use that to derive an unbiased estimate, right? You just shift and we scale that count of the observed counts to get the unbiased estimate. And you can find that the standard deviation of this unbiased estimate is like 1 over epsilon squared log 1 delta, but we have the scaling factor 1 over 1 minus 2q. That's kind of inherent in how we did the bit flipping. But the point is that like Q is small when K is large. So if you have more fake users, intuitively they're providing more noise. And so we can proportionally scale Q to be small. And so increasing the number of fake users actually reduces the scale of error. So this is a theoretical analysis, but it's actually noticeable in our experiments. Right? So like it's not just a theory paper, we have some test results. So how do we perform our experiments? Well, we downloaded a list of English words and then a set of tweets, and we sampled 1 word per tweet. So like, because we're providing privacy on each word or each like element of the domain, that's like tweet privacy, I guess. So the number of users is 3 million, and domain size is 4 times 10 to the 5. And we have the fake user protocol with varying parameter k, the number of fake users per real user. And we have these privacy parameters, epsilon and delta. Right? And then we simulate the parallel counts protocol with the same epsilon and delta, just for comparison. Right, so as we expected, increasing the count of fake users reduces the error, but like up to a point, because it can't be smaller than 1, that scaling factor. You can see it level off as we get from 2 to 4. But there is some like noticeable change in the confidence intervals. And we also plot the confidence bound as red dots. So our actual theoretical analysis is kind of close to actually experiments. And we also compared the two protocols, the Balsa tree protocol based on parallel counts, actually has worse error in our experiments. The difference is an order of magnitude. It's like almost 10 times more. So this comes from the fact that the Cheu protocol is optimal for large histograms, large D, right? So it's good as D goes to infinity because we're independent of that domain size. But actually our domain size here is like smaller than 1 over delta. So like this fake user protocol is actually adding less noise, just the way the parameters line up. Right, so those are the two. Well, the first main property was that we have low message complexity, and 2, when the number of users is sufficiently large. But we have the second property, which is robustness to malicious users. How is that? What do I mean by that? Well, what I mean is that suppose that the last user is malicious. They can send arbitrary messages to the shuffler, which will affect the computation and obviously perform an analyzer. So as a baseline example, suppose you run the randomizer on the wrong value, let's say 1. This means there's going to be some bias towards 1 when maybe there shouldn't be. But there's other attacks, or there may be other attacks than just running the randomizer on the wrong value. Maybe you sample the messages from like some cleverly constructed distribution and like shift the protocol's behavior. Right? And in our fake user protocol, we show that it's robust whenever the parameter k is small. Okay, why is that? Well, remember the analyzer we have just shifts and scales some count of the messages. So T sub j is this count of messages that have a 1 in position j, right? So it's a string, and you're just looking if there's a 1 in that position. And also remember that q is proportional to like 1 over n times 1 over k. So the point is that each message shifts this quantity by 0 or 1. And any user sends k plus 1 messages. So the upshot is that like a corrupt user can only influence by like k plus 1 divided by 1 minus 2q, right? The scaling factor. But this is a constant whenever k is a constant, and n is like sufficiently large to drive down this q to be small. Right? If q is small, then this denominator is like, let's say 0.9, I guess. And you have like k, let's say is 1, you have 2 over 0.9 as like a very small, reasonable constant. Right? So like if the parameters line up, we have good protection against malicious users. But what about other protocols? For example, Cheu's protocol. Well, remember what this protocol is. You're running a counting protocol for each bin in the histogram. So you're sending like a linear number of messages. And each message increments a counter or does nothing. So the unbiased estimate that we get is just a shifted version of that original counter. And so a corrupt user can introduce like a very large amount of error if you're not careful. What you could do is just cap it at n, but really like you're kind of hosed because you can't really do better than like n error, right? Because you just have all your messages say, oh, we all have value 1, and then you can't really do anything about that. And like this vulnerability isn't unique because other protocols also have this kind of property where like if you send more messages, you tend to be more open to attack. Right? You're more vulnerable when you have more messages per user. It's an observational fact. We haven't really proved a lower bound for everything, so that's an interesting open question. But it is like an observation we made. So I've gone over 2 main properties: low message complexity, 2, and robustness. But there are like other secondary properties that I'll take a little bit of time to talk about. It's locally private and it's compressible. What do I mean by locally private? Well, when k is 0, each user is only randomizing your one-hot encoding. And so that's like, and two different encodings differ on two positions. And so that means that like, that's just randomized response. And of course, that's locally private for the right epsilon parameter. Right, so it's 2 times the logarithm of this ratio. The 2 is because of shifting by 2. And so why do we care about this? Aren't we studying the shuffle model? Like this is local privacy, why do we care? Well, it turns out this allows us to study the k equals 0 case, as I kind of hinted at before. So if there are no fake users, we just send one message per user. And so remember that like we had a problem where if we set the parameter wrong, we don't get privacy. But now, like it turns out, we can find out an actual choice of Q that does ensure privacy without having to use fake users. Right, you can patch this hard case with the right choice of Q, and then now we'll only demand a single message per user. Right, and this analysis proceeds by amplification by shuffling. In case you don't know, this means that given a locally private randomizer, the literature has shown that shuffling the outputs of n executions is much more private than the randomizer on its own. The epsilon parameter of the shuffle protocol is much smaller than the local protocol. Specifically, you can look at Feldman, McMillan, and Talmor, and you get this ratio between e to the epsilon sub L and n. So what this means is that you can set epsilon sub L to be very big and still get some kind of reasonable privacy at the output. So if you want epsilon sub S delta shuffle privacy, when k is 0, a large epsilon sub L suffices. So we just do some algebra, plug into the equation, solve for Q. And then after we solve for Q, we get this nice function of epsilon sub L, which is a local privacy. And once we plug in that local privacy parameter, we get our flipping frequency, which is what we need to run the protocol. And we can show that after doing all this math, we get that Q is like 1 over root n instead of 1 over n. So the standard deviation is actually going to be proportional to 1 over n to the 1/4. So that's a little bit worse than the vanishing error that we want, but we're constrained by not having fake users. Right? So the error has a worse dependence on n. Right, so if we allow a little bit worse dependence on n, we get 1 message per user. But other properties exist regarding this protocol. And the second one is compressibility. So as written, the messages are d-bit strings. This could be problematic if d is like very, very big. And the claim is that we can make them shorter. And we have 2 approaches. The first is just to turn the binary strings into lists. And in the other, we just use a sketching technique. So in the first approach, we send only the indices of the set bits and ignore the unset bits. For a fake user, the expected length is d times q. For a real user, the expected length is a little bit different. But the point is that the expected number is bounded by d times q plus 1. And remember, q is like very small. It's like 1 over n, or 1 over kn if you have k users, k fake users per real user. Right, so we have a small expected number of items in our list. If you don't like randomized lengths, you can use a turn-off bound and cap the maximum length with high probability. All right, this should help in fitting your messages in the right payload to send to the network. And that gives you log d times dq plus 1. And dq is d over n, right? Where n is number of users. But if the number of users is not too big, so if this ratio is still large, we can use something called count min from the sketching literature. And this approach increases the number of messages at a modest change in the error. But overall, the communication complexity will be logarithmic in D. So hopefully I have time to go over this, but not. So this protocol, this variation of protocol is the following. We sample hash functions, mapping the domain to a smaller domain. And then we run all these functions on user data, and then compute histograms for each hash function. So the number of messages per user is v times k plus 1, because we're running v histograms. And the length of each message is now a function of hat d instead of d, right? Okay, so like, what happens? Well, what happens is that consider any element in the domain. If there are enough hash functions, there's some hash where there's no collisions, right? So if there's enough hash functions, there won't be any collisions. There's one where there's no collisions. And if that's true for element j, the count of the hash value is precisely the count we want. Otherwise, the count is an overestimate, right? Because of collisions. You have your j's and you have other non-j values that are in the same hash bin. Well, why is this interesting? Well, it's interesting because our overall estimate can just be the minimum of the v estimates, right? If there's a hash function with no collisions, we just take the minimum, and the minimum is the true one. And so we can show that the communication complexity with the right choice of v and hat d is polylogarithmic in domain size and polynomial in 1 over epsilon and log 1 over delta. And we allow, there is like a small change in error, but it's not like too bad. It's just like a different polynomial and polylog in D. All right, so that concludes most of my talk. So like, overall, like we have two protocols with different design goals. One minimizes the asymptotic error, is independent of the domain size, and the other minimizes the number of messages per user. Some two lessons I want to take away from this is that like the observed fact or the observation we make is that message complexity tends to influence manipulability. There may be protocols that break this trend, but so far that seems to be the case. And the second lesson is that we may be able to use some techniques from sketching or streaming that are applicable to a shuffle model. For future work, there might be some interesting lower bounds that like interpolate, as Thomas mentioned, like between these extremes. Maybe like for the right number of bits, we can get this amount of error. But we don't have that yet. And another thing is to have like more experiments. Like the tests we run were on natural language data of a certain form. Maybe the protocol has different behavior on like different like distributions of the data. All right, so thank you for watching, and hopefully you took something away from this talk.